Good morning once more, and welcome to today's very first session. This morning, we begin with the topic on inter-VLAN communication. Inter-VLAN communication. So the forward, by default, layer 2 switching network is a broadcast domain, which brings many problems. Virtual local area networks isolate such broadcast domains, preventing users in different VLANs, from communicating with each other. However, such users sometimes need to communicate. That one is important. That such users sometimes need to communicate, even though they're on different VLANs. And we're going to show you an example. Now, this course describes how to implement inter-VLAN communication. By the end of this chapter, you should be able to, number one, master the methods of implementing inter-VLAN communication, then how to use routers to implement inter-VLAN communication, then how to use layer 3 switches to implement inter-VLAN communication. So I hope you're seeing that we have two ways. You can either use a router or a layer 3 switch to implement inter-VLAN communication. It has to be a layer 3 device either way. And how layer 3 packets are forwarded. How layer 3 packets are forwarded between VLANs. So you should be able to understand that by the end of this chapter. So let's begin with the background. So in real world deployment, different IP address segments are assigned to different VLANs. Please never forget this. So when you're doing subnetting to create different segments, IP segments of your network, remember that each of those segments is going to be placed on a different VLAN. So in real world, that is what we do. What does that mean? Look here. Here we have VLAN 10. We have VLAN 10. VLAN 10 is on this network segment 192.168.10.0/24. Then we have VLAN 20. VLAN 20 is placed on the network segment 192.168.20.0/24. So different VLANs on different network segments. PCs on the same network segment in the same VLAN can directly communicate with each other without the need of a layer 3 forwarding device. This kind of communication is referred to as layer 2 communication. So you're on the same VLAN, same network segment, so you can't be able to communicate. This PC here can be able to communicate with this PC here. Similarly, this PC can be able to communicate with this PC. They're on the same VLAN, same network segment. So you can't have a situation whereby you have VLAN 10, then you're assigning these PCs different IPs from different network segments. That one is not acceptable. Inter-VLAN communication belongs to layer 3 communication, which then demands that you use a what? A layer 3 device. The layer 3 device can be a router or a layer 3 switch. Those are the only two layer 3 devices that we have. Okay. So again, sorry, I said we have layer 3 switches and routers only, but we also have firewalls that can act as layer 3 devices and can support layer 3 forwarding. Firewalls. Firewalls specifically, or their main purpose is security. They create a security wall between your intranet and the extranet, which is the internet, between the private and the public network. So that the firewall normally is put at the egress of your intranet, the core layer. Inter-VLAN communication is implemented by connecting a layer 2 switch to a layer 3 interface of a layer 3 device. As you can see here, we have a router, which is a layer 3 device, and we have a layer 2 switch. So in our layer 2 switch, we have created VLAN 10 and VLAN 20. So all the interfaces on our layer 2 switch are layer 2 interfaces. On the other hand, we have layer 3 interfaces on the router. So layer 3 interfaces like that. So if this PC needs to communicate to this PC, that communication will go like this. It will go to the switch, then the switch will forward it to the layer 3 device. Layer 3 device will forward it back to the switch, then the switch will forward it to this device. Is that clear? Yeah, so inter-VLAN communication has to go through a layer 3 device. So that's what you're really supposed to understand here. It has to go through a layer 3 device. Okay. So we have two ways in which we can be able to use layer 3 interfaces to support inter-VLAN communication. One of the way in which we can do that is by using, okay, let me just begin from the top here. Layer 3 interfaces of the router function as gateways. They function as gateways to forward traffic from local network segments to other network segments. So what does that mean? Access devices must be configured with what we call the default gateway IP address. All access devices, if we want to support them to communicate with devices from different network segments, we have to configure what? A default gateway. The only time we don't configure a default gateway is if we just want them to communicate with devices from the same network segment. Are you together? Now, this default gateway normally is the IP address of a layer 3 device that is going to route that particular packet to a different network segment. Is that clear? In this particular case, we have it. We have this interface here that is the gateway of this network segment. And we have this interface here that is the gateway of this network segment. Now, as you might already have guessed, the gateway must be within the same network. The gateway address must be within the same network as the device's IP address. Are we together? Excuse me. They have to be on the same network segments. They have to be on the same. So .20.2, then this one .20.254. Are they on the same network segments? Yes or no? Are they on the same network segments? Yes, they're on the same network segments. So they have to be on the same network segment. Okay, so layer 3 interfaces of the router cannot process. This one is important. Layer 3 interfaces of the router cannot process data with VLAN tags. Therefore, the interfaces of the switch connected to the router must be set to what? Must be set to what? So what that means is this, 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 this link and that link, they have to be access links. How to do that? How do you configure that? You configure this interface as an access interface and this one as an access interface. Port link type, access. Now, one physical interface of the router can function as the gateway of only one VLAN. This is important. One physical interface, gateway to only one VLAN, right? Why do you think that is so? Why do you think one interface, one VLAN? From my preceding explanation, why do you think one interface, one VLAN? Yes, Sylvia. Huh. Mm, mm, yeah, that's very true, by the way. That's very true. So Luyo is saying, that's not what I had thought about, by the way, but Luyo is saying because the access interface here can only allow packets from a single VLAN. See, when it receives a tagged packet, it's going to untag it, right? Yeah, and it only untags those ones for VLAN 10. Any other, then it will discard, right? Yeah. So that's true. The other reason is because of what I told you, that the gateway must be on the same network segment as the access device's IP address. And we said each VLAN on each network segment, right? Yeah, so because you have to configure an IP address on the interface. So one interface of the router can function as the gateway of only one VLAN, meaning that the number of required physical interfaces are determined by what? The quantity of deployed VLANs. Now, as we know, especially routers, here we're using routers physical interfaces. Routers, one of their shortcomings is that they come with few physical interfaces, right? Like the one we have, how many interfaces did it have? How many physical interfaces did it have? Huh? There was the router. There were 6, eh? So you see, 6 or 8 there, something like that. So normally, so that then will dictate that we cannot have more than 6 VLANs in our network, which might not be an ideal situation. Okay, so a router mainly forwarding packets at layer 3 provides only a small number of physical interfaces. Therefore, the scalability of this solution is what? Poor. This solution, look, this solution is like this. For this solution, we are saying each VLAN occupies or uses a single router's physical interface. VLAN 10 is using GE001. VLAN 20 is using G002. So scalability is poor because this router only has 6 physical interfaces. So it means we cannot have more than 6 VLANs, which might not be able to support the requirements of today's networks. Now, the alternative option is using what we call routers sub-interfaces. Routers, sub-interfaces. Routers, sub-interfaces. A sub-interface is a logical interface created on a router's Ethernet interface. So it's a logical. It is identified by a physical interface number. So it has two things, the physical interface number and a sub-interface number. Sub-interface number. So similar to physical interface, a sub-interface can perform layer 3 forwarding. It can perform layer 3 forwarding. Different from a physical interface, a sub-interface can terminate data frames with VLAN tags. Remember, in the preceding slide, we said layer 3 interfaces cannot process VLAN tags, right? Are you together? But now here we are saying, if we break the interface into several sub-interfaces, then the sub-interface can be able to process VLAN tags. That's simply what we are saying. How do we break up a physical interface into multiple sub-interfaces? So we have an interface like G0/0/1. So this one, we can break it into G01.10. So this is the physical interface number, and this is the sub-interface number. Similarly, we can create G0/0/1/20, like that. So you can create multiple sub-interfaces on one physical interface. After connecting the physical interface to the trunk interface of the switch, the physical interface can provide layer 3 forwarding services for multiple VLANs. Now that's the other important thing to mention, that when you're using routers sub-interfaces, then the interconnection between the router and the switch must be configured as a what? Must be configured as a what? As a trunk. Are you together? You remember Luyo's explanation in the preceding slide? That we configured those as access, so that because layer 3 interfaces cannot process VLAN tags, so that this we are configuring it as access so that it can remove the tag before forwarding the packet to the layer 3 physical interface. So that's why we were configuring it as an access interface. But we are saying sub-interfaces can process VLAN tags. So that means that the interconnection between the router and the switch has to be configured as a trunk port. A trunk port. So don't forget that. They have to be configured as a trunk port. Okay. Okay. So let me just write this. Layer 3 sub-interfaces do not support VLAN packets. Discard them once received. So VLAN tags need to be removed from the packets on the sub-interface. Therefore, VLAN tag termination is required. So from what I have already explained, I know this can sound a little bit confusing. This can sound a little bit confusing, whatever is here. That layer 3 subinterfaces do not support VLAN packets. They will discard them if they receive them. Therefore, you need what we call VLAN tags need to be removed from the packets on the subinterface. So you need what is called VLAN tag termination. VLAN tag termination. So let me see how I can explain this. So PC1 wants to communicate with PC2. So look here what happens. PC1 sends the data frame to switch 1. At this particular point, is the frame tagged or untagged? PC1 sends a data frame to switch 1. Is that frame tagged or untagged? Does it have a tag? Untagged, right? Because access devices do not deal with tagged frames. So it gets to switch 1. What will switch 1 do to it on this particular interface that is configured with a PVID of 10? It will tag it, right? It will tag it. Now, after tagging it, it will send it to this trunk port, which allows VLAN 10 and VLAN 20 to pass through, right? So it's going to send it to the router, to this sub interface, because that is the gateway. So this is the gateway, right? So at this point, is this frame tagged or untagged? It is tagged, right? Because when a tagged frame is allowed to pass through a trunk port, then it goes as a tagged frame, right? Very well. Now, when it reaches here on this sub interface GE001.10, when it reaches here, this particular sub interface, the first thing it will do is to remove that tag. So that is what we call VLAN tag termination. We are terminating the tag. We are removing it. So that's what we call VLAN tag termination. So after removing the tag, it will simply look at the destination IP address, then route it just like it will do any other IP packet. So it will go to the routing table, find the next hop and the outgoing interface. So on the next hop and outgoing interface, it will see that, hey, if I have a packet that is destined to this network, then the outgoing interface is what? GE0/0/1.20. Are we together? So it's gonna send it. It's gonna send it here to this sub interface. Then this sub interface, as you're going to see in the lab and maybe also on the subsequent slides, we will configure it with what we call a VLAN ID. We will configure it with a VLAN ID. Sub interfaces, we'll configure them with VLAN IDs. So normally we will configure it with VLAN ID 20, VID 20. So this sub interface is now going to tag that packet with a PVID, with a VLAN ID of 20 before sending it out to the switch. Are you getting the point? So at this point, this data frame has a VLAN ID of 20. And therefore, after the switch receives it, it's going to forward it out via all the interfaces with a PVID of 20. And that's how it's going to reach to this particular person. Are we together? At this point, the data frame tagged or untagged? Untagged, right? Yeah, good. So I know I might have explained things that I will explain later, but I hope you get a general picture of how the sub interface first removes the tag, then forwards using the IP routing table, then the outgoing interface will add a different tag, VLAN tag. Are you getting the point? Yeah, so that's what I want you to understand. And you'll understand that better if you watch my my Inter-VLAN Communication Lab video tutorial. Okay, so let's move on. So, okay, so in fact, this is just what I explained to you. So let's see how a sub interface will process a frame. So the interface connecting the switch to the router must be set to a what? The router forwards the received packets to the corresponding sub-interfaces according to the VLAN tags in the packets. Mm. So let's see how that is done. As I said, if if this PC wants to talk to this PC, it's going to send the data frame to the switch on G001, which is the interface that has connected it to here. Then after that, the switch is going to send that particular frame to the trunk interface that is interconnecting it to the layer 3 device, like that. And then it's going to be sent back to the switch via the outgoing interface of that network segment. And finally, it's going to get to this particular PC. So let's read this. Based on the VLAN ID carried in a packet, the device forwards the packet to the corresponding sub-interface for processing. Through sub-interfaces, the device can implement inter-VLAN communication at layer 3. So as I've said, even though it's a single physical interface, we've created some sub-interfaces. And therefore, if you have the outgoing interface as this guy, then it's simply going to be sent to that guy. And it's going to come back like that. So I hope you get a better picture of how the processing is done. So the sub-interface termination, tag termination, happens like this. So a sub-interface implements VLAN tag termination as follows. Number one, removes VLAN tags from the received packets before forwarding or processing the packet. Number two, it will adds VLAN tags to the packets before forwarding the packets. So first remove, then process, then forward. After that, the outgoing interface will add a VLAN tag before forwarding it back to the switch. So that's how sub-interfaces process. That's how they process in order to support inter-VLAN communication. Okay. Okay, waiting for you to finish up those ones that are writing. Okay. So how do we configure subinterfaces? You create a subinterface by simply typing. So for example, we are on R1. So you simply type int G0 stroke 0 stroke 1. Oh, sorry. Just undo that. So R1 on system view, int G0 stroke 0 stroke 1. Then after that, dot, then the subinterface number. Now, for easy memorization, it is recommended that the subinterface number be the same as the VLAN that it supports. So if you're creating a subinterface for VLAN 10, then just let the subinterface number be .10. Are we together? If you're creating one for .20, then let the subinterface number be .20. So again, you can do in R1, you can do int G0 stroke 0 stroke 1.20. So that's how you create subinterfaces. Okay. After you've created a subinterface, you'll get into the subinterface view. So if you're in R1, so for example, you're in R1, so it will appear like gigabit. Let me not write the whole of it. 1.10. So you'll be on the subinterface view. So once you've created a subinterface, you can be able to assign it an IP address just like any other interface, 168.1.254.24. So now this is what will be used. This is what will be used as your gateway for that VLAN. This will be gateway address for your devices on that VLAN. Now, other than that, on the sub interface, you are also expected to use the command ARP broadcast enable. We already understand that when a layer 3 interface receives a broadcast packet, what does it do? It discards it, right? Yeah, but if you want this layer 3 interface to be able to accept layer 3 broadcast packets so that it can be able to respond with the MAC address of, for example, the gateway, then this is the command to do that. ARP broadcast enable. ARP broadcast enable. Now, after doing that, the other thing you are supposed to do is the .1q. .1q. You remember what .1q is? Huh? The VLAN standard is also referred to as the .1q standard, right? In short, I can't remember, it's 802.1q or something in full, but in short, it's referred to as .1q. So .1q termination, then VID 10. .1q termination VID 10. So this command will do VLAN tag termination. When it receives a tagged packet, removes the tag before processing it. When it receives untagged packet, tags the packet with the VLAN ID 10 before sending it out. Are you getting the point? Yeah. Receive, remove before processing. Receive, add before sending it out. So those are the commands for enabling inter-VLAN communication. So remember, you have to do this on this sub-interface and also on the other sub-interface, which is the 20 sub-interface. So that's exactly what is being done. That is exactly what is being done here. So other than using routers, physical interfaces, or sub-interfaces to implement inter-VLAN communication, yes, you have a question. Mm. Oh, when you're configuring the other sub-interface, you have to, when you're configuring the other sub-interface, you have to quit, right? So if you're here, and you want to configure the other sub-interface, there are two ways to do it. You can quit, Q, enter. If you quit, you come back to R1. Then you can do int G 0/0/1 to 0. Enter. So that's the first option. The other option, when you are on any interface, you can move into any other interface without the need for quitting. For example, you can create the other sub-interface like this, .1, .20. Enter, and it gets you to that. Are we together? In fact, you can even create a loop back here, int loop 0, like that. And it's going to get you to loopback 0 view. So when you are inside an interface, you can create another interface without quitting. Have I answered your question? Okay. Okay, so the other way in which you can enable inter-VLAN communication, other than using routers, physical interfaces, and sub-interfaces, is by using a layer 3 switch. So layer 3 switches, on layer 3 switches, you have to create logical interfaces that are called VLAN if interfaces to implement inter-VLAN communication. VLAN if interfaces. So let's see how that is done. So we first need to understand how the communication happens. So this is a layer 3 switch. This is a layer 3 switch. The layer 3 switch has a switching module. So it is on the switching module that you create VLANs or supports VLAN communication. Are we together? Other than the switching module, it also has the routing module. The routing module, you have to create VLAN if interfaces. VLAN if interfaces in order to support inter-VLAN communication. So layer 2 switches only support layer 2 switching functions. Layer 3 switches, on the other hand, they support layer 3 interfaces, such as VLAN if interfaces, as well as functions of layer 2 switches. So VLAN if interface is a layer 3 logical interface that can remove and add VLAN tags. VLAN if interfaces, therefore, can be used to implement inter-VLAN communication. So just like the sub-interfaces, VLAN if interfaces on layer 3 switches can be able to add or remove VLAN tags. VLAN if interfaces number is the same as the ID of its corresponding VLAN. So if you're having VLAN 10, then you create VLAN if 10. You create VLAN if 10 so that they are on the same number. Is that clear? So example of configuring VLAN if interfaces. So it's quite some process, but not very complicated. So we're having two PCs here, PC1 and PC2. They're on different VLANs, VLAN 10 and 20 respectively. We want them to be able to communicate. So again, just like on the just like on the routers interfaces and sub-interfaces, you have to configure what? Default gateways. So these default gateways is the IP address that you're going to give the VLAN if interface. The VLAN if interface. So you see, we have that one, and we have this one for VLAN 20. So those gateway, they are the same. So how do you do this? So you'll have to begin on your switch by creating, let me just type it because those commands are a little bit, they're a little bit small. So you're on switch 1 like that. So you start by creating VLAN 20 and VLAN 10 using the VLAN batch command. So VLAN batch 10, 20 like that. Then after that, you can do, you can go into the particular interface that is connecting PC1 to switch 1 like that. You go into that interface. Then on the interface view, so gigabit Ethernet, just understand that that is that. So on the interface view, we change this port to an access port. So port, link type, access, like that. Then after we are done with that, we can configure this port to be on VLAN 10. So port default VLAN 10 like that. So similarly, you can go to this interface G002 and add it to VLAN 20 using the same command. So you don't have to recreate the VLAN because we are still on switch 1. So just like that. So after you're done with that, then you can be able now to configure VLAN if interface. Configuring VLAN if interfaces. So to do that, you are on switch 1. The command to do that is int VLAN if, then the VLAN if number. As I said earlier, the VLAN if number should always match the corresponding VLAN that it's supporting. So if it's supporting VLAN 10, then just have it as 10. Okay, so after you've created that, it will take you to the VLAN if interface view. So VLAN if 10, like that. And once you're here, you can be able to configure an IP address. So 192.168.10.254.24, just like that. So once you're done, from the same view, you can create VLAN if 20. Then again, you assign it an IP address. So that's how you configure VLAN if interfaces. Okay. So the VLAN if forwarding process, let's try and understand this. Okay, so this example assumes that the required ARP or MAC address entries already exist on the PCs. So we are not going to do an ARP broadcast, and also the layer 3 switch. So the communication process between PC1 and PC2 is as follows. So PC1 performs calculation based on its local IP address and the local subnet mask and destination IP address, and finds that the destination device, PC2, is not on its network segment. So this guy wants to talk to this guy. First thing, inside the PC, compares these two IP addresses. Are they on the same network segment? Are they on the same network segment? Finds out, no, they're not on the same network segment. So what happens? PC1 then determines that layer 3 communication is required and sends the traffic destined for PC2, meaning that the destination IP address is that one, to its gateway. So it's going to send it to its gateway, to 254. So the data frame sent by PC1, the source MAC address is the MAC address of who? Of this one. Are we together? Then the destination MAC address. Destination MAC address will be the MAC address of who? The MAC address of the VLAN if interface. Are we together? The MAC address of the VLAN if interface will be the destination MAC address. So that's the very first point, that you send it to that interface, then it's taken to the VLAN if interface. So let's move forward and see what happens next. Process number 2. So after receiving the packet sent from PC1 to PC2, the switch will decapsulate the packet and find that the destination MAC address is the MAC address of the VLAN if 10. The switch then sends the packet to the routing module for further processing. So the switch will check destination MAC address for the VLAN if, and send it to the VLAN if interface. Step number 3 here, this one here. The routing module finds that the destination IP address is 192.168.20.2, which is not the IP address of its local interface, and determines that this packet needs to be forwarded at layer 3 because they are not on the same network segment. By searching the routing table, the routing module finds a matching route, the direct route generated by VLAN if 20 for this packet. And therefore, it's going to send this packet to VLAN what? 20. I'm going to send it to VLAN 20. Okay. So step number 4 here. Step number 4 is here. Because the matching route is a direct route, the switch determines that the packet has reached the last hop. It's not going to pass through any other router. So it searches its ARP table for 192.168.20.2, obtains the corresponding MAC address, and sends the packet to the switching module for re-encapsulation. So it sends it just as it is to the switching module. Now the switching module searches its MAC address table to determine the outbound interface of the frame and whether the frame needs to carry a VLAN tag. So data frame sent by the switching module, the source MAC address will be the MAC address of VLAN if 10. So we've not changed that. The destination MAC address will be the MAC address of PC2. Yeah, so VLAN tag at point number 5 here, and tagged, right? Good. Okay, so that's the forwarding process of the VLAN tag. So let's look at the layer 3 communication process. This topology is used as an example to describe the communication process from PC1 in VLAN 10 to the server that is on the internet. So we want to understand how this process will happen. So PC1 on VLAN 10 wants to talk to the server on the internet. So this is our PC1. This is the server on the internet. So how will that communication process occur? How will it flow? Okay. So just as before we go into the details, of course, this will get here, tagged or untagged, untagged, right? Then sent to the other switch, tagged or untagged, huh? Tagged or untagged. Interconnection between access switch and aggregation switch. Is this a trunk link or an access link? Eh? It can either be hybrid or trunk, right? So this will be tagged, right? So on switch 2, we've created what? VLAN if 10, VLAN if 20, and VLAN if 30. You can see that PC1 has been configured with a default gateway of 10.254, which is the gateway of VLAN if that one. So after the switch receives it, it's gonna send it. It's gonna send it, of course, to the egress router. Then the router is gonna send it to the ISP. ISP is gonna deliver it to what? Here is the data frame tagged or untagged? Hmm? Tagged or untagged?
Untagged.
Untagged, right? Yes, untagged. Because we are using VLAN if interfaces, so it's going to remove the tag before sending it out to the router. Okay, so let's look into the detail. So the logical connection. Oh, maybe just something else I need to mention. Let me mention something here. When this packet from PC1, when this packet gets here, what is the source IP address? What is the source IP address? The IP address of PC1, right? Right? And this is a what? This is called a private IP address, right? Now, when you're going to the internet, packets that go to the internet have to be routed using a public IP address. Public IP address. For example, maybe 2.2.2.2. So it has to be routed using a public IP address. So normally on this router, we perform what we call NATing. What we call what? NATing. Some people are smiling. What does that mean? Does that have some other funny meaning in Sheng? Eh? Okay, maybe I'll ask one of you during the break. So NATing. So NATing, other than the other Sheng meaning, means network address translation. So we're going to learn more about network address translation and how it's done. But generally, just know that NATing enables the mapping of public and private IP addresses on the router. One of the NATing methods uses what we call port address translation. It's called network address port translation, NAPT. So instead of just using the IP address, it also uses the TCP port numbers to map between public and private IP addresses. So that when you're coming back, when this guy is replying to 2.2.2.2, then this guy is going to look and change that destination address to. Are you getting the point? So normally nothing is implemented at the egress router. The router that is connecting you to your ISP. Okay. Yes. Yes, we are going to learn about that. We're going to learn about it. There's a topic. There's a topic about network address translation. So we're going to learn that. Thank you for asking. Okay. So logical connection between the different devices and the PCs. So we have switch 1 here, and we have the PC1 here that wants to communicate to the internet. So we have to configure a default route on switch 2 to allow internet users to access the internet. Okay. I'm trying to make some sense out of that. Okay, just give me a minute to recollect. On R1, configure static routes to the user network segment of VLAN 10 and VLAN 20 to enable intranet PCs using private IP addresses to access the internet. Configure NAT network address port translation on R1. Okay, so generally we know that here we have two switches, the access layer switch and the aggregation layer switch, switch 1 and switch 2. So for this interface that is that does not have a background color, they are configured as access interfaces, while this one trunk interface. So the interface that connects to the end devices, access, right? Interface that interconnects switch 1 and switch 2, we configure it as trunk like that. Then on the switch will have the routing module. So the routing module, we will create VLAN if interfaces 10, for example, to support PC1. And on this particular interface, we are going to configure an IP address that is going to be used as the gateway address of PC1. Is that clear? Yeah. So other than that, we also said that you have to configure NAT here. You have to configure NAT, and you also have to configure static route. A static route to the user network segment of VLAN 10 and VLAN 20. So you can be able to create that. So that's what we will do. Let's see the communication process. Please try and understand this. So PC processing, before the sending of a packet to that, the PC sends the packet to its gateway after determining that the destination IP address is not on its network segment. So the very first thing the PC will have to do is to check, find out, is this destination IP on my network? And you know how that is done. Okay, so after that, if it's not on my network, I send this packet to my gateway. So in sending it to the gateway, the source MAC address will be my MAC address. Destination MAC address, the MAC address of the gateway. Are we together? Destination MAC address of the gateway. VLAN tag at this point. No VLAN tag, right? Source IP address of PC1. Destination IP address of the what? Server. Okay, let's move on. So after, let me see if I do next. Okay, good. So the switch will receive here. The switch will receive it will receive this particular frame and see that it's supposed to forward. So after receiving the frame, switch 1 will search the MAC address table for the destination MAC address and forward the frame. So the assumption was that they already know, right? They already have the MAC address of the destination, which is this particular gateway's MAC address. So it will simply send it out through the destination is MAC2. So I'll send it out through G0024. Are you seeing that? Are you together? So here, this source MAC address, does it change on switch 1? Doesn't change, right? Destination MAC address, not changed, right? VLAN tag, it has to now be tagged, right? Yeah, with a VLAN ID of 10. So these are nice tagged. Okay, so let's move on. Let's look at process number 3. So at process number 3 here, switch 2 receives this particular frame. It finds that the destination MAC address is the MAC address of the VLAN if 10 and sends the frame to the routing module, which then searches the routing table for the route matching the IP destination of 2.3.4.5. So that's what switch 2 will do. So first of all, find out, hey, do I have this on my routing table? Now, on the routing table, we have configured a default static route. Are you seeing the default static route for this particular switch? If you receive any packet whose destination you do not know, send it to this next hop. The outgoing interface is VLAN if 30. So just send it out. Send it out to this guy. So after finding that the matching route is a default route, the outbound interface is VLAN if 30. And the next hop is 30.2. So switch 2 searches its ARP table to obtain the MAC address of what? Of the corresponding interface. Of this interface. Are you getting the point? So now the destination MAC address will have to change. Are you getting that? The destination MAC address will have to change to the MAC address of this particular interface. So I hope you understand that. Okay. So let's see. Let's see here. So as you can see, switch 2 processing. After finding the MAC address corresponding to the next hop, switch 2 replaces the source MAC address of the packet with the MAC address of VLAN if 30 and forwards the packet to the switching module. So the source MAC address now is the MAC address of VLAN if 30. So that's the outgoing interface. Yeah, so we use that MAC address. And the destination MAC address changes to the MAC address of this interface. Are we together? MAC3. Are you seeing that? MAC3. Then it also removes what? The VLAN tag. It removes the VLAN tag. Source IP address, has it changed? Destination IP address, has it changed? Yeah? No, right? No for both of them. Okay. So number 5, R1 processing. So R1 will check the destination MAC address of the data packet and find that the MAC address belongs to its interface, G000. So it will check the destination IP address, find that it's not a local IP address, therefore it will search its routing table, then find a default matching route and forward the packet to a carrier device while performing NAT, network address translation, to translate the source IP address and port number of the packet. So on this router, we will have configured a default route to the ISP router. I'll send it to the ISP, and then the ISP will find the server. Other than that, we will also perform NATing on R1. Okay. So that is the communication process. That is the communication process of that particular scenario that we've seen there. Anyone with a question? Anyone with a question?
Yeah, sorry.
Yes, please go ahead, Maurice.
Just wanted to know the maximum number of sub-interfaces one can actually configure.
Oh, the maximum number.
Yeah.
I'm not really sure. What I know is that you can configure as many as possible. But we are going for a break right now. Let me give you that assignment to search on the maximum number of sub-interfaces that can be created on a physical interface. Then when we come back, please share it with us. Is that okay, Maurice?
Yeah, let me search. Let me try to do some.
Okay. Okay. Thank you very much. Thank you very much. Okay. So guys, asanteni sana.